Okay, so today what I wanted to do is to show you a bit of the flavor of the general theory that you can use to prove the things that I mentioned yesterday. And so today there's nothing to do with Φ43, basically. It's completely general theory, which doesn't refer to this at all. And remember I mentioned that the basic idea is to describe functions or distributions locally, just like what you do for smooth functions by a Taylor series, but where you replace polynomials by other things. Okay? And these other things would then eventually be random, and they would be built from the noise. But for the moment, so today I want to just essentially think about what's the natural way of generalizing Taylor series. Okay? So, of course, so let me just write down for a smooth function, right? So for a smooth function, you know that f of y is about f of x, and then you have f prime of x, y minus x, and let me write two terms, f second of x over 2 times y minus x square. And so if we want to generalize this, the first thing we need is we need to have some vector space in which we plug these coefficients, right? So here the Taylor series, it essentially consists of 2 bits, right? So there are the coefficients, should be this, and then there are the actual monomials that they multiply, right? So here there would be there's a 1 here. Okay? And so the Taylor expansion really just consists of the blue coefficients, right? And then we know what the monomials are. So the first thing we want is we want a vector space T, okay? And T is just going to be the vector space that holds our coefficients. But it naturally should come with some sort of grading, right? I mean, these coefficients, they are not all made equal. That one corresponds to some kind of order 0 term. That's an order 1 term, order 2, etc., right? And so the vector space T should naturally come with a grading. So it should be a direct sum of some T alphas. And now in the case of Taylor series, the alpha would just be positive integers, or 0. Now in our case, we want to describe distribution, and so it's quite natural to also allow for negative homogeneities or fractional homogeneities, okay? So the alphas will just take values in some index set A, but A doesn't need to be integers, and it doesn't need to be positive, okay? So the only thing that we want is we want it to sort of look like integers, okay? So we don't want accumulation points, and we want it bounded from below. So A and R should be discrete, and it should be bounded from below. Okay. And just for definiteness, let's assume that each of the T alphas is finite dimensional, which would be the case in the usual Taylor expansions, but it's actually not necessary, okay? So it's really, all you need here is a norm for each of them. So there should be Banach spaces, but you should really think of them as finite dimensional. So in the example that we're interested in, they would be finite dimensional, okay? But then there is a second thing about Taylor expansions, right? So of course, at each point, the Taylor expansion would essentially be an element in that space, okay? But now, if you want to talk about regularity, you want to be able to compare Taylor expansions. And in particular, you want to compare Taylor expansions at different points, okay? And now, if you do Taylor expansions at different points, it's not very natural to actually compare the coefficients, right? Because they wouldn't be coefficients for the same monomials. Right? So what you really have to do is you take one of them and you re-expand it around the other point, and then you can compare coefficients, right? That's the natural thing to do. And so what you really want here is you want not just this graded vector space, but you also want a group of transformations acting on that space that you should think of, the operation of re-expanding around a different point. Okay? So so you want a group G, which would be a subgroup of just linear operators from T to T. And, well, so if we want to mimic the properties of the usual Taylor expansions, what property do we want the elements in that group of operators to have? Well, if you take a monomial of, say, degree n, and you just re-expand around a different point, right? So you say you have x minus h to the n. So now I view this as the monomial of degree n based at h. And now I expand it around 0, which just, gives you x to the n minus n, x to the n minus 1h, etc. And so what you see is that, well, obviously the top coefficient doesn't change, right? So you still have the top monomial is the same and with the same coefficient. And then you have lower order monomials appearing with different coefficients. Okay? And so we want to mimic that property. So what does it say? So it says that if you take any operator in G and you take any element from one of these T alphas and you apply gamma to tau, which really corresponds to formally re-expanding around a different point, then you want to basically get tau again. And so if you subtract tau, you want to get only things of lower order. Okay, so you want this to belong to the direct sum of the T betas with beta strictly less than alpha. Okay? So let's call this, we'll say T less than alpha. Okay, so that's natural notation. And okay, so now these two, so this piece of data is what I call a regularity structure. Okay, so that's just an algebraic structure that has properties that are sort of similar to that of the monomials in the Taylor expansion. Well, of course, it doesn't really assume anything. And here it's purely algebraic. It's not an analytical object. It's a purely algebraic object. And these things are just finite dimensional vector spaces. And this would typically be some relatively simple group of linear transformations on these vector spaces. So in the case of the Taylor expansion, we can view this as just being the space of abstract polynomials in whatever many indeterminants you have as dimensions in your space. And then the group G as a group, it would actually just be the group of translations. And it acts on polynomials by just re-expanding around a different point. Okay? So the pair, if you want, T and G, well, or TGA if you add the index set also. It's what I call a regularity structure. But now that you have this abstract structure, you want to kind of realize it concretely. Okay, so you want to say, so if you want, this describes the blue bits. Okay, now you want the description of the red bits in a way. So it describes some of the algebra of the red bits, but it doesn't say anything about what they really are. Okay? So this is what I call a model. So a model, you should think of it as a kind of realization of a regularity structure. Okay? And so what do you want in order to realize such a structure? Well, basically, you want for each element in T, you would want, and each point of your ambient space, you want to prescribe what is the corresponding monomial. Okay, so you want a map that for every point x, so now you fix some ambient space Rd. And in general, so in our case, we would think of Rd as really being space-time. And then it's also natural to fix a scaling, right? Because so in the example we're interested in is a parabolic equation. And so the natural thing would be to endow space-time with the parabolic scaling, which in some sense, as you'll see in a second, kind of says that time counts double in some sense, right? So it would say that the natural distance function on space-time is not given by t minus s plus, say, x minus y, but it would be given by square root of t minus s plus x minus y. Okay, so that's the natural parabolic distance between space-time points. Okay, and the general scaling is simply a bunch of integer values for each direction, and then the natural distance is that for each direction you look at the distance between components and you raise it to the power 1 over that integer value. Okay, so the Euclidean scaling would just be 1s, the parabolic scaling would be 2 for the time direction and 1 for the other directions. And you could have, in the Kawasaki dynamic, where the linear part was a Laplacian square, the natural scaling would be a 4 for the time direction and 1 for the space directions, right? Okay, so you fix yourself one of these scalings, and now you want to map that at every point, so that's a space-time point, gives you a linear operator that takes an element of t and spits out a distribution in general. Okay? So the pi x at every point x is the thing that really turns an abstract element of t into a concrete distribution, right? So in the case of Taylor polynomials, you should really think of the example where t would just be polynomials in, say, d abstract variables, okay, that commute. And then you should think of pi x of, say, xi to the n as being a function, and it's the function y minus x I to the n. Okay, and if you have a product of things, it would just be the corresponding product of things. Okay, so the pi x is the thing that actually takes, if you want, these coefficients, and then it spits out the actual function that the coefficients correspond to. Okay. But then we want more, because we also want to know how these pi x's fit together. Okay, so we want to know that for any 2 points x and y, we want to have this operation of taking an expansion around one point and re-expanding around the other point. So what it means here is that for any 2 points x and y, we want to give ourselves an element gamma xy of this group G. Okay? And now we want these two objects to, well, the first thing we want is that we want this operation to really correspond to taking an expansion around y, re-expanding around x. And what this means is that we would want pi x composed with gamma xy to be equal to pi y, okay, for any 2 points x and y. And this makes sense, right? So pi is a linear map from t to s prime. Gamma is an element of G, but G is a subspace, is a subset of just linear maps from t to t. Okay, so you can compose to the right with an element of G. And naturally, we would also want that gamma xy, gamma yz is gamma xz, which, if pi is somehow faithful in a way, this of course implies this, but in general, you know, pi mapping everything to 0 would be allowed, and then this doesn't imply, right? So we just impose it as a separate condition. But now we would also want these indices to really represent kind of homogeneities, right? So at the moment, everything is still kind of purely algebraic. There's no analytical condition on anything. Okay, so now we would want to impose analytical conditions that would really say that, you know, something of degree 2, well, what does it mean to be of degree 2? It essentially means that you vanish for the 2 at the point x. Okay, so we want to encode this. So we would like to say that if you apply the pi x to an element in T alpha, you get something that vanishes at order alpha at x. Okay? But the thing is, these guys, they are distributions. So you cannot say that it vanishes by simply imposing, say, absolute value of this less than y minus x to the alpha, because it doesn't make any sense to evaluate at a point. So the natural thing to do is you take an element in T alpha, you look at pi x tau, that's a distribution. So the only thing you can do is test it against test functions. And what I'm going to do is I test it against the test function, which is essentially localized around the point x. Okay? So when I write phi x lambda, it really means that you take your favorite nice compactly supported smooth test function and you translate it so it's centered around x, and you rescale it so that the typical size of the support is lambda. And here is where the scaling comes in, which is that, for example, in the case of parabolic scaling, in the time direction, you rescale by lambda square rather than lambda. Okay, so here, for example, if there was a time direction, you would rescale by lambda square, if that's the time, or lambda 4 in the case of the Kawasaki dynamic. Okay? So this is what I mean by phi x lambda. And now, for the monomials, and vertically you scale it like a delta function. Okay, so vertically you scale it in such a way that the integral doesn't change, doesn't depend on lambda. Okay? And if you do that, well, integrating a monomial of degree n against an approximate delta function is essentially going to give you a multiple of lambda to the n. Okay, so that's quite easy to check. And so the natural thing to impose here is that when you test this against one of these localized test functions, you get something of order lambda to the alpha. Okay? And of course, sort of times it's linear, so say norm of tau equal to 1. And you would want this to be uniform over, well, so there are three things, right? There's lambda, the test function of the point x. So in lambda, you would want it to be uniform in, say, 0, 1. So it's only a small lambda condition. It's not a large lambda condition. You want it to be locally uniform in x. So it's a local theory. It doesn't care about what happens at infinity. And you want it to be uniform over phi's in some reasonable set, right? So you say, take phi which has support in the ball of radius 1 and which has sufficiently many derivatives bounded by 1. Yes?
So lambda is going to be scaling.
Yeah.
Does it somehow depend on x or?
No, so you want this to be true for every lambda and every x, right? Which is exactly what you would have for the monomials, right? So you take a... Well, so the important thing is that the x here is the same as the x here, right? So if you take the pi x, which would kind of correspond to the monomial based at x, then you only test it against test functions that are themselves, localized around x. Okay, so it doesn't tell you anything about what you get if you test it against the test function, which is localized around a different point. Or it would give you something, actually, because the test function localized around a different point, you can always view it as some very large number times the test function, which is in my class and localized around x, but then it would give you some very bad bounds. Okay, so you have a good bound only if you test it against something which is localized at x. No, just upper bound. Yeah, only upper bound. So it's perfectly allowed to be 0. Right? And then the other natural condition, so we want some condition on the gammas as well. Right? So what's the natural condition on the gammas? Well, so if you apply gamma to your tau, sorry, just tau is still the same guy in one of these T alphas. Well, then you get tau itself plus stuff in the lower order spaces. So say you look at the size of the component in T beta. So I write, say, norm with a beta. That really just means, it's not a Hölder norm or anything. So this really just means this guy is an element of T and just means the component in the beta, in the T beta. Okay? And so what's the natural thing to impose here? Well, just think about what happens when you re-expand the monomial, right? So if you if you take the monomial of degree n and you re-expand around a point which is nearby, and you ask yourself what's going to be the coefficient in front of x to the m for m less than n, it's going to be essentially the distance between the points to the power n minus m, right? And then some binomial coefficient in front. So the sum of the two powers is always going to be basically the degree of the monomial you started from. And so it's natural here to impose the same thing, which is that the gamma xy, we assume that it's bounded by x minus y to the power, the difference between this homogeneity and this homogeneity here. Okay, so it's alpha minus beta. And so here beta is always strictly less than alpha, so this exponent here is always automatically positive. Okay, so that's for beta less than alpha. And again, we want this locally uniform for x and y, and say x and y distance less than 1 from each other. Okay, so now, so this is a model. So once we have this, now in principle, well, we would like to be able to describe objects using such a model. Okay? So the usual way we think about Taylor expansions is we think of a function f as being given, okay? And then you compute its Taylor expansion. And then you say that my function was really of class C gamma, say, if I'm able to find a Taylor expansion up to order gamma, or, well, integer part of gamma, and then I want the remainder to be of order gamma, okay, x minus y to the gamma. Okay, that's basically what it means to be C gamma. Now, what I want to do here is I want to take sort of the opposite point of view. Okay? So instead of taking the function as being the basic object, you take the Taylor expansion at each point as the basic object. Okay? So you say now, I give myself an f, but now the f that I give myself is just at every point of Rd, or a subset of Rd, I give myself a Taylor expansion, say up to order gamma. Okay, so I take an element of t less than gamma. And so it's sort of like a candidate Taylor expansion, or like a jet. Okay, so you have a jet at each point, if you want. And at the moment, just because you have a jet of order gamma at each point doesn't mean that it represents some C gamma function. Right? So at the moment, it's simply, well, at every point, I give myself a bunch of coefficients, and that's it. And now you would want to have a condition which tells you, do they actually fit together nicely? Right? So what would be the condition which guarantees or which makes it plausible that there really exists an actual function or an actual distribution which looks like this at every point? Okay? So the natural condition, well, the natural condition is that this doesn't change too much, when you move the point. Right? So that's the natural thing that you want. And so what does it mean not to change too much? Well, I'm going to say that f belongs to d gamma, and it's d gamma that's really just like C gamma, okay? And it's d just because d comes after C. If when you compare f of x, so you want to compare f of x and f of y, but now f of x represents kind of like a Taylor expansion or a jet at x. F of y is a jet at y. In order to compare them, you have to first re-expand one of them around the other point, right? So the natural thing to do here is to apply gamma xy to f of y. So it takes the jet at y, but re-expands it around x. And now we can compare coefficients. And so take again the component at level alpha for some alpha less than gamma. And now I claim that the natural condition is to impose that this is bounded by some multiple of x minus y to the power gamma minus alpha. Okay, so I claim first that if this whole thing just happens to be the usual Taylor polynomials, then this coincides with the usual C gamma spaces. Okay, except maybe at integer. So at integer values, so the D1 really corresponds to Lipschitz functions and not C1 functions. Okay, but that's really just because we are slightly inconsistent in the way we call sort of C gamma for integer values and non-integer values. So why is that? Well, you see, if you think of this guy, so assume that f represents really a function in C gamma. Okay, so now I claim that this is then true. Right? So how do you see this? Well, if f is in C gamma, so the f really is the Taylor expansion of your C gamma function, okay, up to order gamma. And now take alpha equals 0. So alpha equals 0 is just the coefficient, just the value. And so this is really just the value of f at x. And what is this? Well, it's you take the Taylor series at y, but then you view it as expanded around x, and you take the 0-order coefficient there, okay? Which really means you just take the Taylor expansion at y and you evaluate it at x. Okay, that's all it does. And so then, well, if alpha is equal to 0, that's basically your definition of C gamma, right? So you compare the function of the value of the function with the Taylor expansion, and you get an error of order x minus y to the gamma. And now what about the other values of alpha? Well, at alpha equal 1, this is basically the derivative of your function, right? It's the next coefficient in your Taylor expansion. And this is basically just take your Taylor expansion and take the derivative of the Taylor expansion and look at it at y. Okay. So it's basically exactly the same story, but for the derivative instead of the function itself. And of course, if the function is C gamma, then the derivative is C gamma minus 1. And so you're going to have that bound with alpha equal 1, right? And, well, and so on for all the values of alpha less than gamma, right? And so you see that this is really the same as the usual C gamma spaces, except that here it makes, these guys didn't need to be polynomials. They didn't need to represent even functions or anything, right? So it was completely general. And so now I claim that this is still the right definition in the following sense. That, well, this is the condition that guarantees that you can really glue these things together in order to obtain one single distribution or function, which kind of looks like what it should look like around every point. Okay? So the theorem is that, so first take gamma positive. So one thing that you notice that even if gamma is negative here, this could still be a non-trivial condition, right? Because in here you're allowed to have, in A is allowed to contain negative homogeneities, and so if gamma is somewhere in between, below 0 but still above the most negative guy up there, then this exponent here can still be positive. So this can still be a non-trivial condition, even if things are negative. But so take a gamma which is positive. So then the claim is that there exists a unique map R from D gamma into distributions with the property that if you take R applied to F, so now that's a distribution, okay, and you compare it to pi x f of x, right? So f of x is, if you want your jet at the point x, pi x f of x is the actual distribution that this really corresponds to. And now we want to say that around the point x, this guy is close to that guy, right? And we want it to be, ideally, we'd want to be close up to order gamma. Right? And so the claim is that this, and now again, since they're distributions, the only thing we can do is test against test functions. And you obtain lambda 2 gamma. Okay? Now, So this is true in absolute generality. Okay, so the only thing you need is this kind of structure. Yeah. No, this is a condition. This condition is strong enough to determine R uniquely. You see, uniqueness is actually easy. It's easy to have uniqueness because suppose you have more than one candidate, okay? Then compare the two candidates. You just subtract these two things. The pi x f of x's cancel out, okay? No, but you can't. Because this depends on x. I mean, so this here is a family of distributions, right? So for every point x, this gives you a distribution, and they're all different. And so you want to find one which in some sense is tangent to all of them at every point, right? So it's not, you can't just take one of them, because then it's not going to look like the other one near another point. Okay, so first the uniqueness. So the uniqueness is very easy, right? Because if you had two, the problem is really the existence. Because if you had two candidates, you just, essentially because of this, what you get is that if you had two candidates, Rf and say R bar f, then this would immediately imply that something like this is true, okay? But now this is basically a delta sequence, and this goes to 0 because gamma is positive, okay? And so you can just play around with testing against an arbitrary test function and then viewing this as a mollifier for your arbitrary test function, and you play around a bit and you see that this guy minus that guy tested against an arbitrary test function has to be 0. Okay, and therefore it has to be the 0 distribution. Okay, so the uniqueness is essentially trivial. And the thing which is highly non-trivial is the existence. Okay, so it's not at all clear in principle that such a guy exists. Okay. Now, on the other hand, the existence is still true even if gamma is negative. Okay, but the uniqueness fails. Okay, so if gamma is negative, existence still holds. And you can still make it kind of continuous. Right? So it's not just that there's an axiom of choice thing or whatever. It's an explicit construction, and it's continuous as a function of everything. Now, there's just one sort of slightly subtle point I also want to insist on, is that, so here it looks like a linear map, okay? So in a way, and it is kind of a linear map in the sense that this d gamma is a perfectly nice Banach space, and this is a continuous linear map, or, well, there's the thing about things being local in X, okay, but then it's a Fréchet space where you have semi-norms. And this is a perfectly nice continuous linear operator, okay? Now, what you would want in the end is you want to have stability with respect to approximations. Right? So what this is going to translate into in our context is that we're really going to look at sequences of these models that depend on some cutoff parameter epsilon. Okay? And then we want to have some stability as they converge to a limiting model. Now, in this space of models, there's a natural topology, right? Because, I mean, basically, this defines some kind of a norm, right? Which is just the smallest constant you can put here. And so you also have a natural distance, which is that if you have two models, well, here it always makes sense plugging in just the difference between pi and pi bar, say. And here it also always makes sense plugging in just the difference between gamma and gamma bar, okay? And then you can look at, again, the smallest constants that you can put in here. So there's a natural notion of a distance between two models, okay? And there's also, now, if you change the model, then this space actually changes, right? Because if you change the model, you change these gamma xy's. And so you really end up with a different space here for each model. So the picture here, if you want, is that you have your space of models. So this curly M would be the space of all possible models for a given regularity structure. And then for each model, you have a kind of fiber, which would be the d gamma corresponding to that model. Okay, and that's a linear space. Okay, so for each model, you have a linear space here, which is that d gamma. But the space of models is not linear. Right? The space of models is obviously not linear because being in G is a nonlinear condition. These are nonlinear conditions, right? So that's very much not a linear space. But these are linear spaces. And you can actually compare points that live on different fibers here. Because, the natural thing to do is you just take that expression minus the corresponding expression for the other guy, which is going to have a different gamma, but who cares? And again, you just look at the smallest constant that appears here, right? And it's just typically not going to be 0, but then again, who cares? They live on different fibers, so the distance is not supposed to be 0 anyway. So you have a natural way of comparing things here across fibers. And the claim is that this guy is really continuous, not just within each fiber here, but it's also continuous across fibers. Okay? So it's really a continuous map of this whole big space where you take into account the model and which fiber you're on. Okay? And in that sense, it's actually not a linear map. Okay? So it just happens to be linear on each of these fibers. Okay? But it's really and it's very important that it's continuous on the big space because that's the thing that gives you the instability. Now, there's one particular case in which the R is extremely easy to describe. So I give you the formula for R. Okay, is that so if pi x tau so happens to be a function or a continuous function for each tau, so then there's an extremely simple formula, which is that Rf of x, then Rf is also a function, okay? So Rf is a function. And you have that Rf of x is simply, well, basically the only reasonable thing that it could be, which is you take your kind of your pi x f of x, which is, if you want, your jet at the point x. Now this is a distribution, but it actually it's now a continuous function. And so you can just evaluate that function at x. Right, so that's about the only thing you do, which is in the case of Taylor expansions, it's the completely trivial statement which says that, if you want to recover a function from its Taylor expansion, you just take the first coefficient, right? But here, so first, it's not necessarily just the lowest order coefficients because you can have a whole bunch of negative order coefficients and they would all contribute here, right? So it's like if you want things of positive order will necessarily not contribute because of that condition, right? So this condition will imply that if that guy happens to be if alpha is positive, then if that guy is a continuous function, this tells you that it has to vanish at the point x, and it has to vanish essentially at all alpha. But if alpha is negative, it doesn't tell you that it has to vanish, right? So as soon as alpha is less or equal to 0, it can give you a non-zero contribution. And so typically here you would get a non-zero contribution from all the negative order terms. And the non-trivial fact, again, so here it's a completely trivial identity, if you want. And the non-trivial fact is that this is stable under the topology that I just described, right? And which is really not obvious to see here, because here it's very important that the x, you see the x comes into 3 slots simultaneously somehow, right? And if you change any one of them, then it's not stable anymore, okay? So in a way, it's only sort of simultaneously, it's stable when you plug in the same x in each of the 3 slots. And if you try to fix any one of them, and view this just as, fixing the two other ones, it's not going to be stable. So it's so if you want, that's basically the fundamental result that you use to then, to describe solutions to your equations. Now, so let me give you, okay. So let me show you how multiplication works. Right? So basically now what we want is we want to be able to reformulate our PD as a fixed point problem in one of these spaces. Okay? And that means that we have to reformulate in this context essentially all the operations that you need in order to make sense of the fixed point problem for a PD. Okay, so now if you rewrite your PD with variation of constants formula, then you have something like, right? So if you have a general PD of the form, say dt, or anything of the form LU equal f of u, you have any kind of semi-linear PD of that type, you really reformulate it as u equal to g convolved with f of u, where g is the Green's function for L. Okay, say L is a differential operator with constant coefficients. And so now you want to make sense of this fixed point problem. And so you need to be able to make sense of the operation convolution with g, which would be the heat kernel in our case. And you need to make sense of, whatever nonlinear operations appear in your equation. So there are essentially two things that we need to be able to make sense of. It's multiplication and integration against the heat kernel, convolution with the heat kernel, or with some kernel that has properties similar to those of the heat kernel. And so let me first discuss multiplication. Because now actually in this context, multiplication ends up being the easier operation to make sense of, okay? So first, the whole thing was designed to be able to then just multiply things as if they were normal functions, right? Even though they are not. And so multiplication is going to be relatively easy to make sense of, and actually the harder one becomes integration with respect to the convolution with the heat kernel, which in principle you wouldn't think is very hard, because you'd say, well, it's easy, you just apply this reconstruction operator, you get a distribution, and then you convolve it with the heat kernel. Okay, that's it. You can convolve any distribution with the heat kernel, no problem, right? The problem is that then, you would want, in order to solve your fixed point problem, you want to somewhere gain regularity, right? So you would want the operation of convolution with the heat kernel to map you from one of these d gamma spaces into a better d gamma space, okay? And that's where it becomes very non-trivial. So it means that you have to describe the operation of convolution with the heat kernel at the level of these jets in a non-trivial way, not by just using Taylor expansion, okay? Because that wouldn't give you enough regularity. But, okay, so let's just first discuss multiplication. Multiplication in some sense is now really easy. Essentially, all you have to do is you have to assume, now of course, in practice that might be hard to show depending on how you build these models, okay? But that at this stage, we simply assume that we have a product on T, okay? Multiplication is a pointwise operation. It's a local operation, okay? So at the level of the usual Taylor expansions, okay, if you think the Taylor expansion of a product is actually just the product of the Taylor expansions, okay, in the sense of, well, you multiply two polynomials, you get a polynomial again, okay? It's simply the usual product. And so here it's the same thing. We simply assume that we are given a product that takes two elements of T and spits out a new element of T. And so now all we have to think about is what are the reasonable properties that the product should have, right? So again, if we just take inspiration from the usual Taylor expansions, well, it should map. If you multiply something of homogeneity alpha with something of homogeneity beta, you should get something of homogeneity alpha plus beta. Okay, so that's very reasonable. And then there's a second property that is very reasonable to assume, which is that if you take two expansions around the same point, okay, and you multiply them together, and then you re-expand around a different point, which should really be just exactly the same distribution described in a different way, then you should get the same thing as if you re-expand both of them around the other point and then multiply them. Okay, so that's a very reasonable thing to assume. And so what this means here is that if you take any element of this group G, you should have the property that this applied to a product is just the product of the guys applied to the individual factors. Okay, so it should have this property here, some sort of multiplicative distributional property. Okay? And this is just the abstract way of saying what I just said. Right? It's nothing else. Okay? And so now if you have a product like this, it's trivial to multiply things, right? I mean, so these guys are actual continuous functions, right? They are just continuous functions with values in that finite dimensional vector space. You have a product on that space, and so you can just multiply them pointwise, right? So all you do now is you define, say, f1 times f2 of x pointwise as f1 of x times f2 of x. And the only question that, since the only useful objects for us are in some sense the ones in these d gamma spaces, because that's the ones that we know how to relate to an actual distribution, then the question is, if you take two guys that belong to some of these d gamma spaces, does the pointwise product again belong to some of these d gamma spaces, right? So how does the regularity, if you want, change when you do pointwise multiplication? So what would one guess? So say you take an f1, which is in d gamma 1. Yes? It's essentially built into how you're going to define these guys when you apply them to a product, right? Because here, there's lots of freedom, right? I don't specify anything on how you should define.
So this formula does take an operator product.
So it could, right. So the thing is that it doesn't, you see, these assumptions don't tell you anything about how this guy is supposed to relate, right? So in some sense, you would want to interpret this as being pi x tau times pi x tau bar, but I haven't imposed anything, right? So in some sense, there's quite a lot of rigidity built in, because you want that guy to still satisfy these bounds, and it is imposed onto you how the gamma xy acts on this guy, right? And so sort of this action is imposed onto you, and these bounds are imposed onto you. And so that gives you actually quite a lot of rigidity, okay? So for example, if say you have a model already for a certain space, and now you have sort of two elements in your space, you want to multiply them, but you don't yet have a candidate for the product. You can just add it in, right? So you can just add a new abstract basis element to your space, which you decree to be the product of the first two guys. Okay, so that's not a problem. So at the algebraic level, it's always possible to somehow implement this, because you just add sufficiently many basis vectors, right? So that's not a problem. Then the group G automatically acts on the things that you've added because you have a formula here for it, right? There's no choice on how you extend that. And it automatically satisfies the right bound. So this actually you can check. It works out fine.
So
and
all of this can be done without time, right? You could do this all statically. Maybe try to find a field theory, or just you don't really, you find everything with time, but you could have done statically.
Statically, I wouldn't really know how to write an equation for it in some sense. Right? So, yeah, it's not so clear how to formulate the whole thing as a fixed point problem. As dynamically, it comes out very naturally. Yeah, so just to finish the point here, so if you do this thing about just adding a symbol that represents the product, there's a theorem that tells you that it's always possible to extend your model in a consistent way. So it's always possible to actually, if you want, find a guy here that has the right properties, but it's not unique in any way in general. Okay, so there's also freedom. There is uniqueness if the homogeneity of the product is positive. Okay, so then you have basically no choice. So as soon as you get into positive homogeneity things, everything becomes extremely rigid, and you have no choice anymore at all. As long as you're in negative homogeneity, there's lots of freedom. But there's a theorem that tells you it's always possible to extend it, but there's no canonical choice. And of course, in practice, you want kind of canonical choices, right? And that's where you have to sort of work a bit harder. But now, okay, so you take two guys, one of this d gamma 1, one in d gamma 2. And so what would happen? What would one expect sort of for the pointwise product, right? So you'd want it to be in one of these d gammas. What should be gamma? So of course, the most natural thing to expect would be that gamma is just gamma 1 plus gamma 2, right? Or gamma 1 minimum gamma 2, right? That's what happens for Hölder functions. You get the minimal regularity. In general, you actually get less, and you can't improve upon that. Okay? And so how much less you get depends on what's the lowest homogeneity that appears in the description of these guys. Okay? So I'm going to write a lower subscript here, which just says, so this just means that f1 of x really doesn't just belong to T with things of homogeneity less than gamma 1, but also things, but that everything has also homogeneity bigger or equal to alpha 1. Okay? So if you want if you look at f of x and you look at in which components of T it has non-zero, it's non-vanishing. It's non-vanishing only in components between alpha 1 and gamma 1. Okay, so the thing of lowest homogeneity is alpha 1. Now, for usual functions, that would always be 0, right? Unless the function is identically 0. But for usual functions, if the function is non-zero, then there's going to be somewhere where it has a value, and the value corresponds to something of homogeneity 0, right? So for usual functions, you always have 0 here. But for things describing distributions, this guy could be negative, and this is essentially the order of your distribution, if you want. Right? And so here, what you end up with is that gamma is actually the minimum between gamma 1 plus alpha 2 and gamma 2 plus alpha 1. Okay, and that's so that's quite natural. So you see that for functions, you just get minimum between gamma 1 and gamma 2 because the alphas are 0. Okay? And for distribution, well, it's also natural. It says that, sort of multiplying with a distribution of order -1 is a bit like taking one derivative. So you lose 1 degree of regularity, actually, right? And that's, of course, well known in a way, right? So it's very reasonable to have this as the regularity of the product. Okay? And so now you see how we have a chance of formulating our equation as a fixed point problem, right? Because now we know how much we lose when you take products, okay? And, well, we can hope that convolution with the heat kernel would improve regularity by 2, okay? So that would be Schauder estimate. Okay, and it turns out, and I'm going to talk about this a little bit tomorrow, that you do have a Schauder estimate in this context, okay? So in the sense of these D gamma spaces, you also have a Schauder estimate, okay? So there's a Schauder theorem that tells you that, you can implement the operation convolution with the heat kernel, and it maps you from D gamma to D gamma plus 2. Okay, and that's very non-trivial, because you don't get that by just reconstructing and hitting it with the heat kernel. If you do that, you lose a lot in general. Okay, so there is a Schauder estimate that maps you from D gamma to D gamma plus 2. And now you see, we're going to essentially reformulate our equation of some fixed point problem of the form this way. Now, this guy, we're going to represent it. Well, we know that the noise has regularity.
Oh,
yes.
Yeah,
Yes. So there's the cube here. So we know that this guy, in some sense, has regularity minus 5 half. Right? So there was kind of, so this I mentioned it yesterday. Essentially, there's minus 3 half because of space dimension 3. And then there's another minus 1 because of the time direction, which counts double. Right, so this guy, so now one should think of this guy as kind of belonging to a D minus 5 half, and then, well, actually kind of infinity in a way. So we're going to make that guy belong to a space like this. Now, what this would suggest is that if we're lucky, we can set up a fixed point argument for phi in some D gamma space, and the lowest homogeneity that appears is going to be minus 1 half, right? Because minus 5 half plus 2, basically. Okay? So phi is going to be something like this. So then what do we expect for phi square? Well, phi square would then be in D, well, minus 1 here. And up there, we use that formula. We get basically gamma minus a half. That means that for phi cube, you would expect it to be in D minus 3 half, gamma minus 1. Okay? And then, well, you hit it with the Green's function. You gain 2. Okay? And then you see you're back in business. You've actually, essentially, you're able to build a fixed point map that maps you from a D gamma space into a basically D gamma plus 1. Okay, so you essentially end up gaining 1 degree of regularity from your fixed point map, right? And so then you can imagine that, well, you fiddle around with weights at the origin and so on, and you can turn this gain of 1 into small constant for small times. Okay, so there you have to fiddle. Okay, so tomorrow, what I want to do is first I want to discuss a little bit this Schauder estimate, which is essential here, right? So that you need to somewhere gain. Right? Here it tells you how much you lose when you multiply with something of negative regularity. At some point you have to gain it back. So you need the Schauder estimate. And then I'm going to show, how do you in practice, what is the space T actually going to be in our case, right? So what do you actually take for this space T? What do you take for the group G? What do you take for these things, right? And then how do you build the model? And how do you sort of formulate the renormalization at the level? So the renormalization now all happens at the level of the model. Right. Okay, so I think I'll stop here for today. Thanks.